Welcome to an introduction to sequences. The goals of this video are to define a sequence and also to determine if a given sequence is arithmetic or geometric. A sequence is an ordered list of terms or elements as we see here. And each term in a sequence is identified by its location in the sequence. So a sub 1 is the first term in the sequence. A sub 2 would be the second term, and a sub 3 would be the third term, a sub 4 is the fourth term, and so on. So the subscript tells us which term in the sequence we're referring to. There's also two types of sequences. There's a finite sequence and an infinite sequence. A finite sequence is a sequence that has a specific number of terms, as we see here, and then it stops. An infinite sequence, as we see here, continues on forever, and we know that because of the ... on the right. Both types of sequences can be considered a function, where the domain would be 1, 2, 3, and so on, referring to the position of the term in the sequence, and the range would consist of the set of terms that make up the sequence. And often a sequence is expressed as a rule or formula, as we see here. So the value of n is based upon the term that we're looking for in the sequence. So if we want a sub 1 of the first term, that means n is equal to 1. If we want the third term, that means we're looking for a sub 3, so n is equal to 3. So let's go ahead and practice this. Let's say we want to find the first four terms of these two sequences. That means we want to find a sub 1, a sub 2, a sub 3, and a sub 4. Well, if we want to find a sub 1, that means n is equal to 1. So we have 3 times 1 minus 5, so the first term is equal to negative 2. A sub 2 is telling us that now n is equal to 2, so we have 3 times 2 minus 5. That'd be 6 minus 5, which is equal to 1. And we want to find a sub 3, so now n is equal to 3, so we have 3 times 3 minus 5. 9 minus 5 is equal to 4. And then lastly, a sub 4 means n is equal to 4. So we have 3 times 4 minus 5. That'd be 12 minus 5, which is equal to 7. So the first four terms of the sequence are negative 2, 1, 4, and 7. So in this case, the domain would be 1, 2, 3, 4, and the range would be negative 2, 1, 4, and 7. Let's go ahead and try this again. We want to find a sub 1, a sub 2, a sub 3, and a sub 4. So notice n is now the exponent, so we have 2 to the first plus 1 for a sub 1. That would be 2 plus 1, or 3. For a sub 2, we'll have 2 to the second power plus 1. That's 4 plus 1, or 5. And for a sub 3, we have 2 to the power of 3 plus 1. That would be 8 plus 1, or 9. And then lastly, a sub 4 would be 2 to the fourth plus 1. 2 to the fourth is 16 plus 1, so we have 17. So the first four terms of this sequence would be 3, 5, 9, and 17. Another way to express a sequence is by a recursive formula. And this means that each term in a sequence is based upon previous terms, not the value of n. So if you look at this formula here that generates the terms, if we want to find, let's say, a sub 3, we have to find a sub 3 minus 1, or a sub 2. So a sub 3 is based upon the value of a sub 2. If we wanted a sub 5, then this would be a sub 5 minus 1, or a sub 4. The fifth term is based upon the value of the fourth term. So notice that they give us some extra information here to get us started. We know that a sub 1 is equal to 3. Let's go ahead and find the next two terms. So the first term is equal to 3. Let's see if we can find the next two terms. So if we want to find a sub 2, we know n is equal to 2. So we're going to have 4 times a sub, well, 2 minus 1 would be 1. So we have a sub 1 minus 3. We know the value of a sub 1. It was given to us as 3. So we have 4 times 3 minus 3. So we have 12 minus 3, which is equal to 9. The second term is equal to 9. Let's go ahead and find one more term. A sub 3 is going to be equal to, well, now n is equal to 3. So now we'll have 4 times a sub 3 minus 1. That'll be a sub 2 minus 3. That'll give us 4 times a sub 2, which we just found is equal to 9, and then minus the constant 3. So here we have 4 times 9 is 36 minus 3, so the next term is equal to 33. So as you can see with this process, if we wanted to find, let's say, the fifth term, we would have to keep going here and find the fourth term in order to find the fifth term. This second example of a recursive formula actually requires 2 previous terms. And you can see as they give us the first 2 terms to start. Let's go ahead and give it a try. So we know that the first 2 terms are 1 and 2. So the next term would be a sub 3. So now n is 3. So we have a sub 3 minus 2, that's a sub 1, plus a sub, again, n is still 3, so 3 minus 1 would be a sub 2. Well, a sub 1 is equal to 1, plus a sub 2, which is equal to 2, so we have 3. A sub 3 is equal to 3. Let's go ahead and find one more term. A sub 4 is going to equal a sub 4 minus 2, that's a sub 2, plus a sub 4 minus 1, that's a sub 3. So a sub 4 is equal to a sub 2, which is 2, plus a sub 3, which we just found, is 3. So it's equal to 5. So that's how a recursive formula works. Now we're going to shift gears to talk about 2 different types of sequences. One's an arithmetic sequence and the other is a geometric